Bill Morgan here is a third-year industrial engineering student at UIUC. You can see him driving to class from his apartment. As seen in the video, he's driving on Wright Street, crossing Springfield. Later on in the video, you can see that he is frustrated from having to wait 70 seconds for a red light to go from red to green. And that is a problem, hence the problem description. Traffic flow at the Wright and Springfield intersection experiences moderate traffic flow on a typical afternoon at non-peak hours, where peak traffic occurs around 5 to 6 p.m. The objective of this study is to analyze the traffic flow at the intersection to understand the performance of the intersection. Specifically, we are looking at the traffic flowing from the north and the south on Wright Street. The system is a four-way intersection with 3 possible light configurations on the north-south running lights. Cars arrive at some interval times into either the straight or right turn lane or the left turn lane. The possible light configurations on the right are all green lights, one side green arrow, or both sides green arrow. The one side green arrow is activated only if there is a car waiting in the left turn lane, and the green arrow on both sides activate if there is a car in the left turn lane on each side, both extending the light time. There is a potential for a car turning left to have to wait for oncoming traffic while there is no green arrow, and there is also a potential for a car turning either right or left to have to wait for pedestrians. Both would extend the service time. Traffic running east and west has a fairly consistent runtime on its green lights, so that will determine the red light times on our north-south traffic flow model. Bill thinks it's bogus, so let's do a simulation.
Where'd my bike go? Well, in this model, we're assuming that there's no bikes across the intersection at all. Although we do have a little bit of we account for pedestrians a little bit in having a random time where some of the cars will take an extra random amount of time, roughly 10 seconds to cross because they're being blocked by pedestrians.
Okay, so as you can see here, this is the model that we came up with to simulate the intersection of Wright and Springfield. And as you'll notice right away, it's pretty complicated. There's a lot of arrows going all across the place scheduling different events. So we're gonna try and break it down for you so you can understand a little bit more of what's going on. So here we have a version of the model without all the extra arrows, and this is just the basic skeleton of the model, where at the top we have this cluster of nodes in a semicircle sort of thing. That is what handles all the lights changing from red to green, including all the left turn arrows, which for the left turn arrows, if there's a car in the left turn lane, then that lane will get a left turn arrow at the start of the green light, which lasts for 10 seconds before transitioning to green lights for both lanes on both sides for 20 seconds afterwards. So these nodes up here at the top handle all of those different scenarios, which obviously that triggers all the correct logic that the intersection uses and simulates it in our model correctly and with the correct timings as well. And if you move down to the bottom half of the model, this is the cues. So looking just at the bottom 2 rows, we have the N arrival, NS begin, NS end, NL begin, and NS end, NL end. Those models simulate the north side of the intersection, and it's split into the 2 lanes, the straight lane, where they can turn either straight or turn right, and the left turn lane, which is obviously handled slightly differently. In the real system on the intersection, there's 2 lanes, so we have the 2 cues in our model as well. And these are handled by the same inner arrival time, which is under the node N arrival, and there's a probability there, which I think the probability ended up being 0.234 chance that the car arriving on the north side would choose to turn left versus going straight. And so we actually use the same data and the same inner arrival times as well for the south side of the intersection as well. It's a pretty standard single server queue, except there's 4 of them. So N arrival has a chance to trigger schedule the NL begin node if the NL server, which is the intersection, is not currently busy. And then if it begins service, it'll end service a certain amount of time, a random amount of time later, based on a triangular distribution that we had come up with based on our observed data. And it's the same sort of thing for all the other queues, where it's just a standard arrival with a chance of going into the left turn lane or the straight lane, and then a standard begin service node and a standard end node. Making sure that it's not busy. It also has to check whether or not it currently has a green light or a red light before scheduling that service time. But now with all these extra arrows, you can see there's a lot of interactions between the lanes and obviously from the lights. So starting up with the lights, whenever the lights have a chance to turn green, there's a chance based on those nodes and based on the current state of the system that we may or may not schedule a begin service in any of those lanes based on how the lights turn green and whether or not they're there. This is because it would schedule them all at the same time, and we ran into this problem where it would schedule all of them, and it couldn't check whether or not they were busy because it was checking to schedule all of them at the same time. So it had to change up the logic there a little bit to make that work. And also, you can see two canceling edges in here, and that's to handle the left turn lanes. In the real system, obviously, the left turners will not turn if there's a car that's going to be arriving in the next couple seconds while they're in the middle of their turn. So in this system, it's handled by they'll begin their service, but if a car in the opposite straight lane shows up, that'll cancel their end of service and it'll reset their busyness of that lane so that they will actually stay in the queue in our model the same way as in the real world they would not have begun their turn at all. And there's a couple other interactions where if there's an arrow from NS end, for example, to SL begin, where if the straight cars are done and there's no more straight cars to schedule, then it'll schedule a left turn car on the other side, as you would expect in a real intersection. And now I think we're going to be moving on to the results we got from our model.
So after developing confidence intervals for the average queue size and the average wait time in the system, we were able to determine that the cars that were going straight, either in the north or southbound, in the intersection had a longer wait time and generally had a larger queue size. This would be reflected in the amount of cars going straight instead of turning left. And we can see that cars that are turning left at either north or southbound in the intersection had a smaller wait time into the system.